Let's introduce, this is lecture 15, it's the introduction to the second law. So in the Chengel and Bowles text, we have this chapter 6, which is, I always call it, this is lecture 15. We'll call this is chapter 6. Again, I'm going to do about 4 parts of chapter 6 today, and then we'll finish chapter 6. I'll put together videos to finish chapter 6 on Thursday, the day that we're taking exam 2. Okay? And again, I don't know what the text actually calls it. I call this introduction to the second law. And this is page number 1 of lecture 15. And this is what I call chapter 6. A lot of textbooks, a lot of thermodynamics textbooks will have a chapter like this. The goal here is we kind of explore what brought about the second law, how did we come to the conclusions we did, and a little bit about the history. So this tends to start in the 1700s. At this point, we had a pretty good idea about conservation of energy, not necessarily to the extent we do today. So the first law was kind of defined. The second law, we knew that things like perpetual motion machines didn't really make sense, but we didn't really know. So exactly, we're still trying to figure out, is heat energy, is heat and work the same thing? And we didn't necessarily call it work like we do today. With all that said, we knew, scientists and informed, educated people understood that there was this conservation of energy principle, and that we could propose processes that may not violate a conservation of energy principle, but we knew that they wouldn't just happen or spontaneously, or at least we didn't observe them happening. A favorite example of mine is spontaneous cooling. Let's say that I take a can of Coke, and for me and for somebody that grew up in central Oklahoma, they're all Coke, right? You come to my house and say, hey, would you like a Coke? Sure. Okay, what kind? I'll have a Dr. Pepper, thank you. Yeah, no, they're all Coke, it's just different flavors. But anyways, let's say you sit down, you take out a can of your favorite beverage, and we set it down on the coffee table, and initially it's just a little bit cooler than the ambient air, and then all of a sudden a magical process causes it to cool down spontaneously 10 degrees Fahrenheit. Now here's the thing, we can propose this process, and we can even prove using the first law that it's possible, and my equations aren't displaying, that's annoying. We can even prove that this is possible using the first law. We can say, well, take this can of Coke, and we say, all right, well, if we set up the first law, what crosses the boundary? Well, heat. We're saying it's going to spontaneously lose heat. So minus Q out, and that's the only thing crossing the boundary. So that's N minus I, and that's equal to change. That's just simply M delta U. Okay. And mass is about 12 ounces. We can approximate this as M C sub P delta T because it's liquids. Our text uses C sub P for liquids. Right, and so again we know T2 minus T1 is going to be minus 10 degrees Fahrenheit, or minus 10 Rankins. If C sub P for, this is essentially water, is approximately 1 BTU per pound mass Rankine. I don't know, let's say mass is approximately 0.75 pound mass. So as long as Q out is equal to 0.75 times 1 times 10, so we'll say 7.5 BTUs. As long as this thing loses 7.5 BTUs, first law is satisfied. First law says, yes, this is possible. Absolutely, this can spontaneously cool in the atmosphere with no assistance. And we know that's just, as cool as that would be, we know it's just not going to happen. Okay? So again, while this process may not violate the first law, we know experience tells us it's probably not possible. And the reason it's not possible, we can quantify using what we call the second law of thermodynamics. Okay? So the second law of thermodynamics, how did we arrive at this? And I'm going to show you the second law here in a little bit. But let's talk about what formed it. How did we arrive at this? Because it's not a simple concept. And what we find is the history would tell us that there was a group of scientists and engineers trying to figure out the best, most effective, and most efficient way to get everything they could out of these steam engines. So around the turn of the Industrial Revolution, between the 1700s and the 1800s, we've got this new invention revolutionizing the world, making the Industrial Revolution possible. Put heat into this device and it gives you work output, or power output. And the goal is to get as much power output as you could. And understanding conservation of energy tells me is that, look, I can put, the energy must be conserved. If I put all this heat in, I should be able to get all this work out. And we just couldn't do it. And we're trying to figure out why couldn't we do it. Some famous people working on this subject in this time frame. One of them is Rudolf Clausius. Our good friend Rudolf comes up with this idea, and this is a quote from your text, and it says, "It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a higher temperature body." And what does that mean? Well, and we can talk about this in a second. The other statements, so we typically credit these two statements, the Clausius statement and the Kelvin-Planck statement, as kind of the foundation of the second law. The Kelvin-Planck statement, we credit both Kelvin and Planck as they were both, the legend that I've heard is they were working independently at approximately the same time, came to approximately the same conclusion at about the same time, working independently. So we credit both of them with the idea. And the Kelvin-Planck statement says it is impossible for any device operating in a cycle to receive heat from a single reservoir and produce a net amount of work. And this is the idea of we cannot simply take steam from the outlet of a turbine, reheat it, and run it back through the turbine and continue to extract power output. Why is that? Well, if you look at what this turbine is doing, right, we look at pressure with respect to volume, and so as you run material, steam, high pressure, low specific volume or low volume through this turbine, it's going to expand it. And so this area bound by the curve for this process during this expansion represents the work that we can extract from this turbine. Now, if I heat that substance up, nothing about that heating process is going to increase the pressure, unless I can trap it and allow it to do its own boundary work, or I put work into it to decrease the volume. It's just going to expand if I heat it up. It's going to hold reasonably constant pressure, so it's going to expand. And then I run it back to the turbine, and it's going to expand some more. And then I heat it back up, and then it's going to expand some more, and I heat it back up, and it's going to expand some more through the turbine over and over, and you reach a point where it can't expand anymore, right? To operate in a cycle, I have to somehow get this steam back up to this initial point to get it to operate over and over again. I can only go out here so far before I can no longer operate anymore. If I want this turbine to operate continuously and extract power continuously, my process from the inlet to the outlet needs to include something that gets me back to this inlet state. Then I can operate in this cycle that both Kelvin-Planck and Clausius are talking about. Okay? So, that's kind of where we're headed in an abstract form. Okay? So, we want to quantify things. It's kind of our tendency is we want to quantify so we can actually prove, if you will, or show, or be able to determine, calculate. These are all things that as engineers we really like to do. Chapter 6 in the in the Changle and Bowles text never, to my knowledge, never shows you the second law. This is the second law in its purest, ugliest, rawest differential form. The second law tells me that a change in the entropy, right? Change in the entropy is always going to be greater than what causes the entropy change. So how do we change the entropy of a substance? How do we make the molecules more chaotic? Well, one way is you add heat. So if I take the sum of all of the heat, all of the differential slices of heat that occur to go from state 1 to state 2, then this heat divided by the temperature at which that heat occurs. This quantity is what will cause the entropy to change. And what the second law says that the entropy change, little s here, the entropy change times the mass, this quantity will always be greater than the amount of heat divided by temperature required to cause the entropy change. And there's a limit here. There's an equal to limit. This is a special case. It's the best case scenario where this isn't any larger, it's just equal. This is equal to that. That's the best case scenario. We call that reversible. Okay, so this is the second law. We're going to focus on this in Chapter 7. Don't worry too much about it right now, and we're not going to deal with it. We're going to deal with this term a lot, and we're going to talk about how do I deal with this term algebraically. I'm not going to assume that you are comfortable with partial differential equations, or in this case, differential inequalities. We're going to turn this into an equation. We're going to talk about the rules, and we're going to talk about how do you deal with this quantity. What does this actually represent? And that's all going to be Chapter 7. It's going to be our focus. We'll get there. We're not there yet. We're in Chapter 6. Let's talk about how did we get here? Why is this the case? Right? So what this does, again, the second law does a couple of things for us. It tells us the direction that energy can flow, specifically heat. Heat can only flow up to the point where entropy is being generated, right? And we can't destroy entropy. So it dictates the direction that heat can flow and the amount of heat that can flow in a particular direction. It also tells us that no process can be 100% efficient because, again, this is an inequality. So it means this is always increasing. So it means nothing can ever get back to its initial state. So nothing is ever 100% efficient, realistically. Okay? So how do we do this? Well, we use this quantity we call entropy, which you may have talked about. I hope you talked about in the chemistry class. It's a measure of the chaos or disorder within our system. Okay, so again, before we really dive headfirst into that differential inequality, that is the second law, let's talk about the theory associated with how do we get to the second law, and let's talk about some conceptual cyclic devices that we used to figure out what the second law actually is as a scientific community. So let's talk about some terminology here. Okay. First one is a term we call the thermal energy reservoir. This is a body that can supply or absorb finite amounts of heat. Very important term there. Finite, not infinite. Finite amounts of heat without undergoing a significant change in temperature. We will often call this a reservoir. We're going to talk about sinks and sources a little bit later. I would typically use those terms. We'll talk about why, but reservoir is a perfectly reasonable term. Thermal reservoir, heat reservoir, these are all referring to a thermal energy reservoir. These are typically large when compared to my system. If this represents a system, and the system could even be smaller than that, we're typically talking about very large bodies that can absorb or provide finite amounts of energy, heat, without experiencing a significant temperature change. Now, one thing we know is that marine life, or in any kind of ecosystem, the organisms that evolved to survive in those ecosystems have evolved over a long period of time, millions of years, thousands of millions of years. They are not going to react well to large-scale temperature change. That's what we're going to pick up on the next video.